Yeah? You have reached xi is really xi minus x bar. Right? So now, suppose your data is atypical. Suppose in the set, say what 50 observations of x. Suppose the mean of x is 20. And nearly all values of x are around 20. So some of them are 50, some of them are 25. But one value of x is 70. One value of x is quite atypical. One value of x is quite different from the rest of the values of x. The rest of the values of x are more or less similar. Then how will that value impact the variance of beta at OLS? So for that particular value, suppose that is the second value. For that particular value, x2 minus x bar square will be pretty large. So the variance of beta at OLS will increase that much. Right? So each of these tells you how much that particular value of x contributes, how much that particular, the difference between that particular value of x and the mean value of x contributes to the variance of beta. So each of these numbers are called leverages, because they tell you how much the difference between each value of x and the mean value of x contributes to the variance of beta at OLS. He says if there are values of x which are very atypical, we call them outliers. There is a value of x which is very atypical, right? So suppose you are looking at say you are looking at how much your friends spend, or you might look at say data like so suppose you are looking at what kind of a question can I give you? Right, you are looking at say prices of fruits. So look at prices of mangoes and the qualities of, or that will not be the right question really. You are looking at say maybe the earnings by people and their education levels. And suppose you got people who are generally in your data, everybody is a higher secondary or a graduate and so on and so forth. And right, so everybody is like that. So everybody is between say 4th standard to the, so suppose 4th standard to say the 12th standard. Everybody is like that. But for some reason there is a PhD in that. So one of the guys who is working there has a PhD. Right, and you are measuring education by the years of education. So most of the people there in the data have education levels between 5 years to say 12 years. And you have somebody there whose years of education are 20. How will the inclusion of this person in your data affect your estimates? Is the question that I am throwing at you. Looking at that form. Variance of beta will go up, no? Because for a particular observation, xi minus x bar square will be pretty large. The difference from the mean will be pretty large, and therefore that observation will make a large contribution to the variance of beta hat. So the variance of beta hat will be large, and therefore your type 2 error probability might increase. You might actually find the variable insignificant. So one of the arguments is that there are too many outliers in your data. If there are some outliers in your data, they can actually bias your p-values downwards. So what happens? Do you delete these observations? What happens if you delete this guy? You say you are not included in the data. Please go. What is the impact of that? N goes down. So the variance of beta hat goes up. But summation, one of the observations, the leverages will go down. So whether to drop that person or not depends upon what is your N. If you have lots of observations, then you might probably drop it. Right? But if you have lots of observations, then the impact of that lever, that one particular observation might actually not be so small. So the typical problem in leverage will be small sample. So whether to delete that person or not depends upon what is the impact on the data. Right? If that one particular leverage is so large that you might want to drop in, it might improve your variance of beta hat and so on. Okay, now the point is suppose if all the variances are different, right? If all the variances are different, sigma 1 square, sigma 2 square, sigma 3 square, sigma 4 square are different, then what is suggested, one of the suggestions is, so this will be the correct formula for the variance of beta hat if there is heteroscedasticity, correct formula for the variance of beta hat in the presence of heteroscedasticity. So one of the suggestions is, instead of using sigma 1 square, use E hat 1 square, which is an unbiased estimator of sigma 1 square. It might not be a consistent estimator, it's an unbiased estimator. Do a regression, y is equal to alpha plus beta xi plus ei, get E1 hat, E2 hat, E3 hat, etc. E1 hat is an unbiased estimator of sigma 1 square, E2 hat is an unbiased estimator of sigma 2 square. So the idea is to take estimate the variance of beta hat OLS not by sigma square upon summation xi minus x bar square, but by so simply replace sigma 1 square by E hat 1 square, sigma 2 square by E hat 2 square, sigma 3 square by E hat 3 square. So you will be modifying the formula. So you say this is the correct formula for variance of beta hat. This is called White's heteroscedasticity consistent standard errors. They are called White's heteroscedasticity consistent standard errors. Why are they called heteroscedasticity consistent? Because we are allowing them, because we are deriving the formula without assuming away heteroscedasticity. We derive the formula without assuming away heteroscedasticity. The White's heteroscedasticity consistent variance covariance matrices, or White's heteroscedasticity consistent standard errors. Okay? White's heteroscedasticity consistent standard errors. Sure? That's how you get the. So that's one alternative that can be done. Okay? So the first part is leverages. Leverages into E hat 1 square, E hat 2 square, etc. etc. That is the leverage state of everybody. Right? Because outliers are a fact of life. Small samples, outliers will typically plague you in a lot of primary kind of a research. Yeah, so you need to, if large data, it doesn't really matter. Small data set and outliers matter. Because they increase the variance of beta and then you need to deal with it. And secondly, with heteroscedasticity, you could either do an FGLS or you could do White's heteroscedasticity consistent variance covariance, heteroscedasticity consistent standard errors, variance of beta hat OLS. Is this clear, folks? Difficult or not difficult? Pretty simple. How much more time do we have? 15 minutes. Okay. Now, so we have been able to solve quite a few interesting kind of problems. Right. When you come to instrumental variables, there is one very useful instrumental variable method which is called two-stage least squares. Right. So what Ronak showed to me was actually a two-stage least squares. So I thought I'll as well talk about that. Right. So what you do is so what you do with the data is, suppose yi, alpha plus beta xi plus ei and zi. So suppose yeah, so you need an instrument. So let Z be an instrument because so in the first stage do the following things. See, yeah, and calculate
because the error term was
different. But this is actually different. They're different. Right? So gamma hat set. Then do the following relation. 2. Instead of xi, use x hat I. Instead of xi, use x hat I to estimate beta. So second relation yi is equal to alpha and obtain standard OLS estimates of alpha hat and beta hat. Right, so that's a method. You have to argue to me that this is actually an instrumental variable here. This is called a two-stage research. We are doing regression in 2 stages, right? First we are regressing xi and zi, then we are getting x hat and using x hat in the regression to the original variable. So we are doing a two-stage variable. Tell me why this is an instrumental variable. Because we know that the instrumental variable estimator beta hat iv should have been that should have been the beta hat iv. So if I do beta hat here, now beta hat OLS is covariance yeah. Show me that this is actually an OLS. This actually is a beta hat. This actually is an IV estimator. Show me that this is actually an IV estimator. That is, that estimator and that estimator are the same things. Can you show it to me? Prove it to me. So you have to prove to me that this and this are the same thing. So it's actually a book voucher which Vivek and Machula get. Right? There is one more book voucher waiting. So if you can solve this and show it to me, you will get a. Ronak is not allowed. Because you have already done this. So another gift voucher for a book shop is waiting for you. So prove it. So first step में क्या करेंगे? XI hat. Beta, correct. So you win a book voucher. Both of you will get it on the last lecture, right? So can anybody, can you follow this? It's just a matter of substituting things, no? So you just have to substitute for beta hat. See, what is xi hat? Beta hat zi. Right, so just substitute there, and you will get your answer. Right, this is homework for all of you. I am not going to solve this. This is a simple matter of substitution. But this is a two-stage least squares estimator, which is also an IV estimator. Right, so a two-stage least square estimator is also called, which is also one type of an IV, instrumental variables estimator. Does anybody have any doubts so far about what we have done? Sure. So, if you are saying that a number of transactions a person makes on Paytm, with Paytm, depend upon that person's education level and income level. Right, so you do a regression first, just put an education level thing, and where you measure years of education as, education by the number of years that a person has gone to school or college. And suppose you get a beta hat, right? And suppose that beta hat is something like, say, 0.7. So you say that means the following, that if a person's years of education go by 1, then that person's daily Paytm transactions goes up by 0.7. Right? And then you say that actually, a person's Paytm transaction also depend upon his number of, his income levels. Right? Okay? So you put an income variable. You also do a fresh regression. The Paytm, number of Paytm transactions per day is the left hand side, the right hand side variable the education and income. Now it's